The next question, I believe, let's see what the number is here. I believe on the 429 document, this would be question 6. Okay. It was question 5, I believe, on a previous document, but we didn't get to it on the 427 document. Okay. In any case, our situation is we got a 4 microfarad capacitor charged at 16 volts and a 30 microhenry, our good old 30 microhenry inductor, and we got a switch, so we close the switch. Now what happens? Well, the capacitor is going to drive a current. Okay, the current is I of t. Of course, the capacitor starts driving the current, the inductor starts fighting it. So we have this interplay between the capacitor and the inductor that causes the current to build much less than instantaneously. Okay, and the driving voltage is going to be decreasing, unlike the driving voltage that you would have if you had a constant source here. So the current through the inductor is not going to build exponentially. It's going to kind of exponentially approach the current that you would get from the capacitor, but the current, the voltage in the capacitor keeps decreasing, so you have this exponential that keeps chasing a decreasing voltage. So you end up with something like this, and it's actually going to be, as we'll see, a sine curve as opposed to an exponential approach to a constant voltage. Okay? When you exponentially approach this decreasing voltage in this manner, you get a sine curve. We can easily write the equation for this circuit. We have no voltage, so we just do the voltage drops here. We have no source, so we just have the voltage drop across the resistor and the inductor. A voltage drop, not the resistor, the capacitor in the inductor. The voltage drop across the capacitor is just Q over C, where Q is the charge of the capacitor, and the voltage drop across the inductor is L di dt, the inductance times the rate of change of the current. Now, the current is the rate of change of the charge on the capacitor, as we've seen several times already, so that the di dt becomes a second derivative of Q with respect to t. The derivative of dq dt, which is the current, with respect to t, second derivative of charge with respect to t, and Q over C remains the same, and this is all equal to 0. This very simple differential equation we can easily solve, and I'm not going to go through the details of solving this equation. And we'll go through details in a more complex equation shortly, but on this one I'm just going to leave it to you to do this. If we divide through by L, here's the equation we want to solve. And we solve this by letting Q equal e to the mt or e to the rt, whatever you want, taking the derivative, solving for r, and plugging back in to the e to the rt. In this case, we get an imaginary solution, 1 over the square root of LC for the r, 1 over the square root of LC times I is going to be the solution to the characteristic equation. That's going to give us the charge function, which will be an arbitrary constant times the cosine of omega t plus another arbitrary constant, where omega is 1 over the square root of LC, or the square root of 1 over LC. Now, this is completely analogous to the equation that we solved in mechanics last semester for a harmonic oscillator, where we had restoring force negative kx, which is equal to the mass times the acceleration being second derivative of x with respect to t. The equation that we get is then mass times second derivative of the position with respect to time, plus kx equals 0. We divide both sides by the mass. We get this equation, and this leads to this solution, a cosine of omega t plus theta naught, where omega is the square root of k over m. Completely analogous differential equations, the only difference being the k over m as opposed to the 1 over LC and q instead of x. So the solution is, in all respects, of the identical nature, just the omega now has a different meaning and a different interpretation. So that's our solution. And recall that this solution led us to the reference circle picture, where the harmonic motion is a projection on a line of the motion of a point moving around a reference circle of radius a with angular frequency omega, and starting at some theta naught position on the reference circle. All that applies here as well, and we'll get into that. But now the immediate question was, what is the frequency of this oscillation? We see from the differential equation that we have an oscillatory solution, a cosine solution. What's the frequency? Well, the angular frequency is going to be 1 over the square root of LC. LC multiplies out to 4 times 30 micros squared, which is going to be 120 times 10 to the negative 12th, or 1.2 times 10 to the negative 10th. You can check the units. The units of henries times farads are seconds squared, so that what we get is reciprocal seconds. Interpret this as radians per second because of the nature of the solution, the oscillatory, the cosine solution. And this comes out approximately 9 times 10 to the 4th when you do the reciprocal of the square root of 1.2 times 10 to the negative 10th. So here's the frequency of our solution. So this circuit is going to naturally oscillate at 90,000 radians per second. The frequency itself will be this divided by 2 pi, because every radian, well, we're talking about the number of radians per second on a unit circle or a reference circle picture. It takes 2 pi radians to complete a cycle. So we divide the 9 times 10 to the 4th radians per second by 2 pi radians per cycle and get approximately 1.5 times 10 to the 4th, or 15,000 cycles per second. So that'll be our frequency. Now we're going to go on with more interpretation of this circuit and a little more explanation perhaps of what's going on.